All right, everybody, back again. We're trying to get into the next bit of organic chemistry. In this part, we're going to talk about stereochemistry. And let me give you just a heads up on this. I'm going to be able to use the whiteboard to do some drawing, but at the end of the day, a lot of students, I don't want to say most or less than, I don't know, but a lot of students actually need a model kit in order to really start to see molecules in 3 dimensions, to really be able to understand what they're seeing when you look at a projection that uses wedges and dashes. At the end of the day, this is a big topic. There's not a lot of information in the topic, but it takes a lot of practice to be able to see molecules in 3 dimensions. And so you have to work with these models. You have to work with the process in order to be able to get a hang of it. Very few students. I mean, I have seen a few, like a couple, but very few students can just see it right away. Like have a very excellent, uncanny ability to visualize things in 3 dimensions. I wasn't one of those students. It took me a long time to practice seeing things in order to kind of get a feel for that. So let's take a look at what I'm talking about and we'll get into it. All right, so at the end of the day, what we're talking about are molecules that have carbons, and here's my prototypical carbon. It's carbons that have tetrahedral centers. But those tetrahedral centers are connected to four different groups. Let's try this again here. Draw this framework out, try to draw it a little better. Okay, so let me take a break to talk about what I mean. Molecules that have carbons that have tetrahedral centers, and where those tetrahedral carbons are connected to 4 different groups, that carbon becomes handed. And what I mean by handed is literally like your hands. There's a left hand and a right hand, and they're not the same. They're mirror images of each other, and not only are they mirror images of each other, they're non-superimposable. And so what that means is that there's nothing you can do with your hands. There's nothing that you can do in order to get the left hand to be exactly like the right hand. The best you can do is flip it around and say, well, the palm is facing that way towards the camera. This palm is facing away from the camera. I can't flip it over to have the palms facing the same way and then have my fingers lined up. It's because they actually are different versions of each other. And this is ultimately what we're talking about when it comes to chiral carbons. And the word is chiral. And so your hands are chiral. And so a chiral is an object that is chiral has a non-superimposable mirror image. And so let me write that down real quick. An object that is chiral has a non-superimposable mirror image. This is something that's chiral. The thing that is the non-superimposable mirror image of another molecule. And so what we're talking about here are let's try to think about it from the standpoint of isomers. We're talking about molecules that have the same formula, but some sort of different structure. What kind of isomers have we talked about? We've talked about isomers that are conformational isomers. And so we take a molecule like C7H16, and we can arrange the different carbons in lots of different ways. And so those we say are constitutional isomers. Same formula, different connectivity. Then we talked about rotational conformations, and maybe you could say that a rotational conformation of an alkane, maybe in a way it's an isomer. Thinking that, well, if you were to freeze frame a molecule with one particular dihedral angle, adjust that, then you have a similar idea. Now we're starting to get into a different type of isomers. What we're talking about specifically are stereo isomers. So they have the same formula, and in this case, they have the same connectivity as well. So they have the same atoms connected to each other, but then they have a different three-dimensional structure. So it's an isomer. It's the same formula, different shape. How is the shape different? It's not connected differently. It's actually a different three-dimensional projection. So when I think about something that is chiral, an object that is chiral has a non-superimposable mirror image. What that means, the object that is the mirror image that's non-superimposable is called the enantiomer. The enantiomer is the non-superimposable mirror image isomer. So for the very first part of all this chapter, what we're going to do is we're going to discuss all of the different ways to consider non-superimposable mirror image isomers. And then what we're going to do at that point is sort of, go through some other possibilities. There is a possibility when we have a non-superimposable, non-mirror image isomer, and we'll get a little bit more detail into that later on. But let's start off with this group. If I were to create 4 different groups, and in this case, I'm just going to use the colors to represent that. Then what I've done right now with this particular molecule that has a tetrahedral center is I've drawn 2 mirror images of themselves, and they're non-superimposable. There's nothing that you can do with A to rotate it in such a way that it makes it look exactly like B. They actually are mirror images. There's my fake mirror. And they can't superimpose. And so these are enantiomers of each other. What are some objects that are chiral in everyday life? We already talked about hands. And so, we talk about some different geometric shapes, and let me give you some ideas. Is a cylinder a non-superimposable, is it an isomer? Is it chiral? No, it's not chiral. It has a mirror image that is superimposable. But if I make it a coffee cup and I put some sort of symbol on one side of it, then all of a sudden it is chiral, because there's nothing you can do to take its mirror image and rotate it so that it's not that it's superimposable. Another good example I like to use is my prototypical nail. Is a nail chiral? And this is a terrible idea of a nail. This is a more looks like a tack, but let's call it a nail. Is the nail chiral? Well, you should come up with the conclusion that no, it's not chiral. It has a mirror image, but the mirror image is also superimposable. But what can we do to the nail to make it chiral? Well, we can go from a nail to a screw. The screw is definitely chiral because of the way the spiral around the threads goes in one direction. If we take the mirror image, then the mirror image goes in the other direction, and we can't rotate it so that they're exactly the same. So what that means is that there are objects, so at the end of the day, there are objects in the world that are chiral, that have mirror images that are non-superimposable. One of those objects are molecules. And so we're taking a look at this whole section of videos, there probably will end up being two, is a discussion about non-superimposable mirror image isomers and how we can deal with that. Now, we've already discussed one type of isomer, one type of stereoisomer, and that's a cis-trans isomer when it comes to alkenes. We decided that because there is no free rotation around a double bond, that even though the connectivity is the same, in other words, all of the atoms are connected to the same atoms, the difference is in the three-dimensional structure. So these are a type of stereoisomers. They're, in this particular limited case, we're talking about cis-trans isomers, with trans being on the top in this example and cis being on the bottom. There's going to be some different situations when we have to replace one of those hydrogens with another group. Then all of a sudden cis and trans don't really make sense, and so we have to kind of get at a different way to look at those stereoisomers, and so we'll talk about that actually later in later chapters, in later sections. And so what we want to talk about are specifically carbons that have tetrahedral centers, where those tetrahedral centers are connected to 4 different groups. And so one of the things that we have to be able to do, the very first thing that we have to be able to do, is identify carbons that have these tetrahedral centers. So when I draw a molecule like this on the page, it's straightforward to see that I've drawn 4 different colored dots. So I apologize to my colorblind viewers. And so, I can do something like X, X, Y, A, B, A, B, X, Y. Either way you look at it, or whatever device you decide to use, whether it's letters or colors, this is a simplistic version, and it's quite straightforward to identify that the 4 things are different. And so the molecule at that location must be chiral. The molecule is chiral and the carbon is chiral. However, I don't often present molecules to you with the complete 3-dimensional structure shown. In other words, sometimes I just use stick models. So one of the things that you have to be able to do is identify locations where there's chiral carbons. And so this is an important piece of your skill set. This is the very first thing that you're going to be able to do, or that you're going to need to be able to practice doing when you're working with stereoisomers, is identifying carbons and molecules that have chiral centers. So in this particular example, there's more than one carbon that is chiral. And so what I would say is identify all the chiral centers. And so let's try to figure out real quick, let's use this example to decide where the chiral centers are. And so remember, at the end of the day, we're counting the number of groups, and then we're finding groups carbons that have 4 different groups. So what can we rule out right away? Well, right away, we can rule out any carbon that has a double bond or a triple bond, right? Because the basic idea is that the carbon that is chiral has a tetrahedral center. If the carbon has a double bond or it has a triple bond, they're not tetrahedral. They're trigonal planar and they're linear, respectively. And in that case, their mirror images are superimposable, so they don't fit the definition of being chiral. So we can immediately rule out double bonds, and we can immediately rule out triple bonds. The next thing that we can rule out are tetrahedral centers where there's more than one hydrogen. And so it's my opinion that the easiest way to think about chiral carbons is when you're identifying them, is to rule out carbons that are CH2s and CH3s, because then that helps you focus on the other parts of the molecule. You should become immediately familiar with recognizing CH2 and CH3 groups, and then focus your time, because in an exam or quiz, you're only going to have a limited amount of time. Focus that time on the spots where there are other groups or other things other than having 2 CH2s, or excuse me, having 2 or 3 hydrogens. So let's take a look and let's see if we can pick out the locations that have 2 or 3 hydrogens, and that way we can immediately eliminate them, and we'll examine only the things that remain. So at this point, there's a CH3 group, so we're going to eliminate that. There's a CH2 group, we'll eliminate that. There's a CH3, we'll eliminate that. There's a CH2, we'll eliminate that. A CH3, eliminate that. And here are 2 other CH3s, we'll eliminate both of those. The last things then that we'll have to consider are that carbon, and that carbon. And we want to ask ourselves, are they chiral? And so what I'm going to do is I'm going to back up the drawing because it's gotten a little messy. I'm going to take off the X's in the boxes, and then we'll examine each group, each of the carbons that are in the square boxes individually, and we'll see what's going on with each one of those. Okay. So let's take a look at this carbon first. What is that carbon connected to? Well, on one side, it's connected to a CH3 group. On the other side, it's connected to a CH2, CH3. And on the other side, it's connected to a much larger chain. And I'm not going to draw out the condensed structure in this case. What's the 4th group that it's connected to that's not shown, of course? It's a hydrogen. And so when we look at this carbon, we see that it's connected to a hydrogen, an ethyl, a methyl, and then usually I just say something like, and this mess. And those 4 things are not the same. Since those 4 groups are not the same, we can conclude that this is a chiral carbon. So that means it actually exists as 2 different enantiomers. There are 2 different enantiomers representing the 2 different possible 3-dimensional arrangements of that particular carbon. Now, that is not shown in this molecule. In this molecule, no specific stereo information is provided because I didn't use wedges or dashes. And so all you're able to do at this point is say, this is a chiral carbon. You haven't specified which one it is. And so all I can do is say it's chiral. And so I know that there are two different versions of that particular stereo center. Okay. And so let's take a look at another spot. What about this one? Let's take a look at that one. What's it connected to? Well, it's carbon connected to, again, really it's just to say this mess. It's connected to an isopropyl group. It's connected to an ethyl group, and it's connected to a hydrogen. Those four things are different. And so at the end of the day, this is also a chiral carbon. So far I've identified two stereo centers. What about the third carbon that we had in a box earlier? This one here. Is this one a chiral carbon? Well, what's it connected to? It's connected to a ethyl group here. It's connected, oh, excuse me, it's more than an ethyl group. It's all of this mess. It's connected to a methyl group there, a methyl group there, and a hydrogen. That's only three different groups. Because the two methyl groups are identical, turns out that this carbon is not chiral. So at the end of the day, there are only two different chiral carbons in the molecule, this one and this one. And so one of the questions I'll eventually want you to be able to answer is, well, how many different versions are there? Well, let's take a look. There's a left-handed and a right-handed version for this one, as well as a left-handed and right-handed version for that one. And I'm going to use left-handed and right-handed to go back to the analogy of the hands, to go back to the idea that they're non-superimposable mirror images, and then ultimately, because that's how we're actually going to describe them. We're going to describe them using Latin words that stand for left-handed, left and right. We're going to use R and S as the signifiers for each configuration of a chiral carbon. A chiral carbon can be either R or S, and the Latin words are sinister and rictus, I believe is the R one. And so rictus means right, sinister means left, and so this is usually the point in the semester when I say, think about all of the different ways that, think about how the folks in Rome thought about people who were left-handed. Think about how that word has come into the English language. What do we think about sinister now, right? So if you're left-handed, that originally comes from Latin. The word describing left meant sinister, and all the way forward to modern times, the implication is someone who is left-handed is sinister, or that they're evil and somehow, because that's what we've decided the word sinister actually means. And so let's take a look. Each of the two carbons have a possibility, and the possibilities are left and right. So one possibility is the molecule could have one right and one left. The other possibility is one left and one right. And I'm talking about the different carbons here. So this would be, I'm just going to arbitrarily call them carbon 1 and carbon 2. Another possibility is that they're both right, and the other possibility is that they're both left. And so this actually leads us to a formula that says the total number of possible stereoisomers is equal to 2 to the n, where n equals the number of stereocenters. And so in this case, it would be 2 to the 2 equals 4. And we could also, so then if we thought about it and there were 3, it would be 2 to the 3. That equals 8 possibilities. And so you see that just like when you have the number of carbons and the different possible ways to arrange them in constitutional isomers, you quickly get a number of constitutional isomers that gets crazy based on just a few extra carbons. The same thing sort of happens with chiral centers. Once you have 3 or 4 chiral centers, the number of possible stereoisomers really starts to get large. So if you had 2 to the 4th, then what do you have? 16 possibilities. And so it goes up quite quickly. All right, so let's stop there. Let's take a quick break and let's do some different examples. Let's do an example where we're going to identify chiral centers. And so let's take a look at something like let's take a look at this. Where are all the chiral centers? Can we identify all the different chiral centers? So at this point, what I would like to do is remind you that we can eliminate any carbons that have double bonds, triple bonds, that are CH2 groups or that are CH3 groups. Well, here's a CH3 at the bottom that we don't have to look at. And of course, at the end, there is also a CH3 group on that side chain. Well, where are all the CH2 groups? There's a CH2 group, there's a CH2 group, and there's a CH2 group. And of course, I'll remind you, there's a carbon with a double bond and there's a carbon with a double bond. We don't have to look at those. So what are the carbons that we should identify, where we should examine to see if they're chiral? That one, that one, that one, and that one. So let's examine them one at a time. Let's start from left and let's go right. So what about the first one? What's it connected to? Well, it's connected to an OH, and I'm just going to call that the rest of the stuff. And then what else is connected to that spot? Well, the carbon has 4 bonds. Of course, then the 4 bonds they're connected to is, the other 2 are hydrogen. So OH is different than the rest of the stuff, which is different than a hydrogen. But since we have 2 hydrogens, that's not 4 different groups. So this one isn't chiral. So that carbon number 1 is not chiral. What about this second carbon? And I'm not numbering the chain or the molecule. I'm just identifying the carbons that we're looking at. Let's take a look and see what that one is. Well, it's this carbon, and it's connected to an OH group here. What else is it connected to? It's connected to a hydrogen that's not shown. So let's take a look. It's connected to this CH2OH group, and then it's connected to the rest of this ring. Those are 4 demonstratively different groups. And so this chiral actually is, this carbon is chiral. So not chiral for this one, but chiral here. Well, what about carbon 3? All right, and so this is where the first little bit of confusion comes in for students. They say, well, it's around a ring. And if I look around the ring clockwise, it's a CH2 group. And if I look around the ring counterclockwise, it's also a CH2 group. So let's draw out the things that it's connected to. It's connected to this OH group. It's connected to a hydrogen. But if I look around the ring, it's connected to a CH2 group. And a lot of students often say, well, those are the same. So they're not, so then that carbon is not chiral. But that's not really the way to look at it. In order for it to be the same, to be considered the same in a ring, it has to be identical all the way around the ring. So yes, it's a CH2 group there, but we have to continue to look around the ring to see what other things are connected. The CH2 group in the clockwise direction is connected to this stuff. the CH2 group in the counterclockwise direction is connected to that stuff. And those two things aren't the same. In other words, around the ring, you do not get the same groups. Because you don't get the same groups, then these two CH2s and the other groups that they're connected to are not the same. And since they're not the same, we would say that carbon number 3, yeah, it's also chiral. Well, what about this 4th carbon? Let's take a look at that one. What's its story? What's its situation? What is it connected to? It's connected to an ethyl group, a hydrogen, and the other two things around the ring. But we don't have to really make a decision because one of them is a CH2 group and one of them is C with a double bond, and those are definitely different. And so this carbon is also chiral because it's connected to 4 different groups. And so what you're going to have to do is you're going to have to be able to take a look at different molecules, and you're going to have to be able to identify the different types of carbons and see if